So I haven't made too much progress, but I just want to take a look at some of the over engineering that's been done on this. Um, so first, this rod, that's not just the threaded rod; it's a ball thread. So here's another one. This is a shorter one, but if you look closely at the thread, this is rounded here. It's not flat. So inside that, in the ball thread, inside the nut, inside there is a ball bearing. So that allows it to reduce the friction and get really close and eliminate backlash. When you turn this to move this forward and then you want to turn it back, you don't want any gaps in there. You want it to start moving back almost immediately, and that's what a ball thread does, is it eliminates backlash. But I do like these rods. They are engineered rods. They've got multiple different kinds of thread, as you can see. So what this is for is, on this side, there's a bearing that goes in here, and then there's just a C-clip that holds that in. And on the other side, where you've got the drive motor, there's another bearing, and this is a bigger bearing because it needs to take a bigger load where the motor is. And this is a fairly wide bearing, and that'll come across here. And then to hold that in is we have this nut, but you can't tighten it too tight because it'll put friction on the bearing. So it has a set screw to hold it in place, and that's what holds the back bearing in place. And then to attach something to this, there's this aluminum block, can go on here, that bolts into it, and now the whole thing can move back and forth. But the problem is it can also move this way, and you need to stabilize it so it doesn't, and that's why we have this rod here. So then I've got these brackets that I printed that hold the 12 millimeter rod. And here's another one. Because again, you need a 12 millimeter stainless steel rod in order to support the massive weight of a shot glass. Of course you do. And sitting on top of this rod is one of these, which is a linear bearing. And if you look inside there, you can actually see the bearings down there. So when you put the rod in, right, so if I put it here, I can put, I put a lot of weight on it, and it's not going to bind. It still moves back and forth. So that's the rods on this thing, and all being driven through a flexible coupling, which is here, attached to a NEMA 17 motor. NEMA 17 being 1.7 inches across. There's also a NEMA 23, and there's NEMA 35s for the bigger motors. But NEMA just gives you the size of the faceplate. As you can see, these are both NEMA 17 motors, and they're very different. And this rod is, it's called a 1204, and what that means is it has a 4 millimeter pitch on the blades. You can see the 4 millimeters and a 12 millimeter diameter, hence 1204. And there's different sizes. There's this one too. As you can see, that one's it's a heftier rod. So this one's a 1605, so 16 millimeter diameter with a 5 millimeter pitch on the thread. So we have those connected to the motors through a flexible coupling. This motor can do 200 steps per revolution, so 1.8 degrees per step. If you look at here's the specs for the stepper motor. So this is basically how it's wired. It has two coils. Actually, inside this, since it's a 200 step, there's each one of these is actually 100 coils and 100 coils. So there's 100 A coils and 100 B coils, and they're all connected together. So if we look at our reference for stepper motors, we can see here's the sequence that you have to take of energizing the coils in order to take a step. So here we can see step 1, we're going clockwise. Step 1 is A is forward polarized, B is forward polarized. Step 2, we flip A to be reverse polarized, B stays the same. In step 3, we keep A the same and we flip B to reverse. And in step 4, we keep B the same and we flip A to reverse. And to go counterclockwise, you just reverse the sequence. So in order to make the motor take a step, you have to go through that sequence of four, I guess, sub-steps. I don't know why they call them steps, because it's each step is a step, and then it takes 4 sub-steps to make a step. So there's 200 permanent magnets around here. There's 100 coils of A, 100 coils of B, and every time you go through that sequence, the motor takes 1 step, which in this case is a 200-step motor. So if we look at the spec, we can see 1.8 degrees per step. So that's 200 steps in 360. Right, so that's how that works. But if we look at the other specs, so it's got a resistance of each one of those coils, each phase is 1.4 ohms. It has an inductance of 3 millihenries and a maximum current of 2 amps. And then it says your rated voltage is 2.8 volts. So all that is, you've got a resistance of 1.4 ohms, and if you put 2.8 volts across that load, it'll drive 2 amps. So that's just a calculated number, 2.8. But if we actually try to drive this motor with 2.8 volts, it's not going to work very well. And the reason for that is these coils, as we know, coils take a bit of time for the current to ramp up. So if we look at a graph of what the current in a coil looks like, when we turn the switch on and the current starts flowing, it takes this amount of time to ramp up. Each one of these divisions here is a time constant. The time constant for series inductive circuits is calculated as L over R. L being the inductance in henries and R being the resistance in ohms. So if we look at, let's see. So if we do our time constant tau equals L over R, we know L is 3 millihenries from our spec sheet. Right, we see 3 millihenries, resistance is 1.4, so over 1.4, and I believe that gives us 2.14 milliseconds. So going back to the graph, each one of these divisions is 2.14 milliseconds. So in order for the coil to actually do its job, it needs the current flowing. So we want to get to 95%, and that'll take 3 time constants. So that'll take 2.14 times 3, so about 6. But as we saw from the card, it takes 4 steps or sub-steps of charging the coils to make 1 step. So that's 4 of those. So we've got 6 times 4. It takes 24 milliseconds to make 1 step. So we've got 24 milliseconds times 200 equals divided by 1,000 to give us seconds. So 4.8 seconds to make a complete revolution. So what that means is each revolution, as we saw, it was a 4 millimeter pitch. So to move this forward by 4 millimeters, we need to make 1 revolution of the motor, which, as we calculated, takes 4.8 seconds. So if I want to move this distance of 400 millimeters, because this whole shaft is 500, so let's say this is 400, so that's 100 revolutions. So that would be 480 seconds to move this from here to here if we were using 2.8 volts. So we can't do that. But this graph tells us how fast we're going to ramp up the current to the maximum steady state current, which is the 100%. So in our case with 2.8 volts, this is the 2 amp line right here, and we're ramping up to 2 amps or to 95% of it within 3 time constants. However, if we made this a higher current, so let's say we applied 12 volts across that 1.4, we'd get 8.5 amps. So if this was 8.5, if 100 was 8.5, getting to 2 amps will happen right around here somewhere. So, you know, a much shorter time. This is 1 time constant, and getting up to 2 amps will happen in here somewhere, which we can't really tell from this graph. To find out the exact time when that happens, we'd have to do the math, which, you know, we won't. On second thought, why not? We're going to do it. Okay, so this graph and this graph, this one is just 1 minus this graph here. Right, so that's pretty easy. And we know this is a decay, so it'll be something like e to the minus x, this curve right here. So if we look at our inductance charging, we will have our instantaneous current, the current here, is equal to the steady state current, which is that current here, times 1 minus e to the, and x would be the number of time constants. So t, time in seconds, over tau, our time constant. So this will tell us how many time constants. We know we want this to be 2 amps. We know at 12 volts, this is 8.5 amps. We're trying to calculate t, that's what we want. And we know our tau is our 2.14 milliseconds. So we just need to turn this into where we're solving for t. So 1 minus e to the minus t over tau is equal to I over I, which means minus e to the minus t over tau is equal to I over I minus 1. E to the minus t over tau is equal to 1 minus I over I. Right, we just subtract that, multiply by 1 both sides. And now to get rid of the exponent here in the e, we take the natural logarithm. So minus t over tau is equal to ln 1 minus I over I. Therefore, time is equal to minus tau ln 1 minus I over I. And now we just plug in our numbers. So t is equal to minus 2.14 times the ln of 1 minus 2 over 8.5. And that's easy enough to calculate. Okay, so we've got 2.2 divided by 8.5 is equal to 0.23, make that negative, add 1, and we take the ln of that, so that's minus 2.6 times minus 2.14, the minus will cancel out, so 2.14 equals 0.57 milliseconds. So we know that it's going to take about half a millisecond for 2 amps to ramp up into that coil. And that'll give us the maximum torque in the shorter amount of time. And I may even recalculate that for 15.4 volts because I'm going to have a 15 volt rail to drive the cooling systems. So I may even try 15 volts with the steppers. Now, of course, the problem is that you can't exceed 2 amps inside this. So at 12 volts, if we don't do anything and just keep feeding 12 volts into it, we're going to get 8 amps going through each coil, and it's going to fry really quick. So what we need is to limit the current to a maximum of 2 amps, and we have a way of doing that. So to drive the stepper, we have to polarize these coils forward and reverse. So how do we do that? That's with a device called an H-bridge, and as you can see here, it's kind of shaped like an H. And if you close these switches, S1 and S4, you can see the current goes this way, and if you open those and close the other two, it goes in the opposite direction. So that's how we reverse it, except they're not switches, they're transistors. And the device that does that is one of these. This is a L298N dual H bridge, so it has two of those bridges, and you can see the output here. There's the output of one, there's the output of the second one, and that's where you feed your voltage in for your motor. So that's the device that does it, but that one doesn't limit the current, as we need to limit it to 2 amps, and this device here is doing that. It's limiting the current, but it also does some other functions that actually allows us to eliminate this H bridge. It has a different kind of thing built in, so we can get rid of this big one and replace it with a small one and have the advantage of current limiting. It can be adjusted here by that little pot. Anyway, this is a A4988 stepper driver, which includes a bunch of functions, so it's a pretty cool thing. The other device we use here is that sensor down there. That's a Hall sensor, and what that does is it senses a magnetic field. And I don't know, you can't really see that, but there's a magnet stuck to the bottom of this, and that's what the sensor is detecting. So here's another one set up, and this is a Hall effect transistor, and that's what senses the magnetic field, and then it turns on a switch and it does a bunch of stuff, and this light comes on when it detects a magnetic field, and also the signal comes out here that I can feed into my controller. So here I have a neodymium magnet that's just on the end of a steel rod, and the light should come on when the magnet gets detected, and oh, nothing happens. Gee whiz. You know what? Let's switch that magnet around. And bingo. So this one only detects south poles. There are other ones that only detect north poles, but the point is they only detect one side of the magnet. So you have to make sure that it's oriented correctly, but you can see as I start getting close, the light comes on, and I can come in from the top. So this can be used to sense a whole bunch of stuff. Every time the magnet goes by, it pulses. Anyway, that's what's being used to detect the home position of the device. Is there's the Hall sensor with a magnet on the bottom of the trolley there. So all that leads us to the final over-engineering on how accurate this thing is when it absolutely doesn't need to be. So I've got the motor now hooked up to this rotary encoder, so that just sends a pulse every time I turn it, and that every click of this should be one step on the motor. So we can see how accurate this thing is. So we move this to the enable position, and when I turn this, the motor turns one step. So you can see that every time, and it does that little vibration thing, not because of the motor, but the rotary encoder is a cheap Chinese thing. It's like 80 cents, so not good quality, but, and then I can go in the other direction by turning the knob the other way or this way. I can go backwards or forwards. So each step is 1/200th of a full rotation, 1.8 degrees. A full rotation moves this forward by 4 millimeters. So that means that every step can position this to within 1/50th of 1 millimeter and move back and forth. You can't see it moving, but because of the zero backlash on the ball thread, I can move it forward one step and backward one step, and it is actually moving 1/50th of a millimeter back and forth, back and forth. So there we go. A completely over-engineered transport system for a shot glass that has to be positioned within a centimeter. Thank you very much.